So with with AI though, transitioning back to that, we've talked a little bit about the pathway and the trajectory of what that's looked like, and the fact this has been a evolution over some time. Now, as you look at it, since you've been involved in it for quite some time, where has it moved very quickly, and where have you seen it kind of stagnate, not taking out 2022, the past maybe 5-7 years where there's really been some major steps?
Well, I'm bringing up my little timeline of just language models here because I like to refer back to it. The very first language models for computers were called a bag of words and word embeddings. That was all the way back to the 40s, 50s, and 60s, right? Because we didn't have deep learning yet. And then we had something called a co-occurrence matrix in the 70s. And finally, we had some deep learning in the early 80s, including CNNs, RNNs, and LSTMs, right? And backpropagation. So we already understood backpropagation, CNNs and RNNs, and I won't get into what all of those mean today. But those are used today in large language models, which are really based on an RNN model in the end. And so
if somebody has no idea what that is, in layman's terms, what are we talking
in layman's terms. So
I think now the digital acumen of people, generally they understand the concept of deep learning, but
all right, real simple. Yeah, let's deconstruct it really, really simply. So what I want to build is a neural net. And for a long time, we could build just shallow neural nets, but they've been getting deeper and deeper. And finally, they could get very deep by 2012 when we solved some math that allowed us to go to now millions of layers if that's what we wanted to do. What is a deep learning neural net, basically? So what the computer does is it figures out by itself decision points, and then it weights a neuron, if you will, to get to the next decision point. So if this were me and I'm looking at Christopher, I can make decisions that it's Christopher. I can look at the hair on his head. I can look at his eyebrows. I can look at his eyes.
The lack of hair on my head.
Yeah. That's fair. That's a decision point, right? And in fact, I can describe those decision points. And what I'm actually doing even here is I'm weighting those. I'm going, his eyes are this blue. They're a little more blue than someone else I know, right? So that's a decision point. Maybe he has earbuds.
Going through this process.
So actually, our neurons do that, and they do it very, very quickly, right? So a neural net is based on the way we think humans may work. Now, I can describe a lot of my points in the middle, but for a computer neural net, we call them hidden layers, and they're hidden because there's basically
we don't know what it's doing. This is the black box in some ways.
I mean, we could go try to deconstruct it, but there's no English equivalent of what it's doing. That's the problem. Like I can put into language. I can describe your mustache in a language, right? I can describe that you do have a mustache. You probably combed it just before we went on the air. It's kind of brown, doesn't have a lot of gray, right?
Yeah.
I have descriptions of it, right?
You have words, you have language to describe what it is.
It does
thereby being able to explain how you use that to discern I'm talking to Christopher Lind.
Exactly. A neural net doesn't have the English language to use in that way, but it is still making those kinds of decisions. And it may make other decisions that we couldn't possibly understand anyway. An earlobe that's a little different than another one or whatever it is, right? Really fascinating. So these are the hidden layers. So basically you have an input layer, a bunch of hidden layers, and an output layer. And all the thing does is add as many layers as it needs in order to differentiate Christopher from Kevin, from Jim, from Betty, from Bill, from Sue. Okay. And however many millions of people. So these can get very, very deep. And we got, really good at image recognition once we had really deep capability. If you'll notice, one of the things that's happened over the years is, people are going, wow, these algorithms are just amazing now. Well, they've kind of followed our compute capability. It's not that we couldn't have possibly done the math to do a deep neural net.
We just didn't have the computing power.
Well, it would have taken 10 years to run. So why would you bother?
Yeah.
It was not a useful model. But finally,
it wasn't practical. It wasn't practical.
By 2012,
to go through all that just to distinguish, is this a cat?
That's right. It was dumb.
Why would we waste that kind of time?
By the way, we had facial recognition. The FBI had facial recognition in the 60s. But it was using, what they would use is they'd look at a face and the computer would say, what's the the space between the eyes, and then the eyes to the nose would draw a triangle, and then the nose to the mouth, and it would do all of these kinds of vector kinds of things, right? And that's how in shape of the head and stuff like that. So it's not that we haven't had facial recognition. It was actually, it worked quite well. Now we can recognize based on billions of characteristics instead of 10 characteristics, right? Or 12, 20 characteristics.
Yeah, it's no, again, going back to similar to kind of some of the things we're talking about, the trajectory of how things have changed was before you had a very predictable, these are the data points on a face that we're looking at, narrow it down to see how accurate. And it was, I mean, really, especially when you study the human head, it's a pretty predictable way to be able to do it. But
it
now
really well for the FBI for 50 years.
Yeah, it worked very well for them. It's just now we have the computing power to assess and analyze so many more data points to come in.
That's right. And a lot of those are hidden layers.